Hi everyone. In this talk, we will discuss the complexity landscape of distributed locally checkable problems on trees. We consider the well-known local model of distributed computing, where the input graph and the communication network are identical. The communication proceeds in synchronous rounds. Local computation power and message size are unbounded. There are two variants of the local model, the deterministic one and the randomized one. In the deterministic variant, each vertex has a unique ID of O of log n bits. In the randomized variant, there is no ID. Each vertex is allowed to generate random bits, and the maximum allowed failure probability is 1 over poly n. The difference between the deterministic model and the randomized model is important, but it is not important to today's talk. Since there is no restriction on the message size, in k rounds, each vertex can gather all information within its distance k neighborhood. In fact, a convenient alternative definition of the local model is that a k-round local algorithm is simply a function that maps each radius k subgraph to an output label. Therefore, in this sense, the local model captures only the locality aspect of distributed computing and nothing else. Computational complexity theory is a branch of theoretical computer science that focuses on classifying the problems into complexity classes according to their difficulty, and relating these classes to each other. That is, the subject of research is sets of problems, not individual problems. There are a lot of distributed problems, but many of them are not interesting in the local model. In particular, it is possible to construct an artificial distributed problem to realize any reasonable given round complexity function. Therefore, if we want to build an interesting computational complexity theory for the local model, it is important that we restrict ourselves to an interesting subclass of distributed problems and get rid of those uninteresting problems. One popular way to do so is to consider the class of problems whose solution is locally checkable. Note that the concept of locally checkable labeling is, in some sense, analogous to the complexity class NP in the sequential setting. The concept of locally checkable labeling was formalized by Nauer and Stockmeyer a long time ago, but a more systematic study of this subject started only a few years ago. An interesting finding of this line of research is the existence of large gaps in the landscape of round complexity. For example, Chan, Kopelowitz, and Petty showed that any deterministic algorithm that solves an LCL problem in sublogarithmic round unbounded degree graphs can be transformed into a deterministic algorithm that takes only O of log star n rounds. And so, in this sense, there is a gap between log star n and log n in the deterministic setting. Here, the notation TLLL refers to the randomized round complexity of distributed low-pass local lemma unbounded degree graphs. Due to the recent breakthrough of deterministic polylogarithmic network decomposition by Rozon and Ghaffari, distributed low-pass local lemma unbounded degree graphs can be solved in poly of log n rounds. And there is still a gap between the upper bound and the log n lower bound. In today's talk, we will focus on trees. The main difference between trees and general graphs is at the higher end of the spectrum. That is, when the round complexity is above log n. Chang and Petty showed the existence of the gap between log n and polynomial in n. And they also showed that for each positive integer k, there is an LCL problem with complexity n to the power of 1 over k. And it was left as an open question whether there are gaps between these complexity classes. Later, Baliu et al. Showed the existence of a gap between square root of n and linear in n. The main contribution of our work is to resolve this open question completely. We extend the result of Baliu et al. To show that there are indeed gaps between these complexity classes. The proof of our result can be seen as a unification of the approaches taken in the Chang-Petty paper and the Baliu et al. Paper. A bipolar tree is a tree with two designated vertices. An important tool used in the proof for the complexity gaps on trees is an equivalence relation on bipolar trees. The precise definition of this relation is quite technical, and so I cannot present it here. But the main idea is the following. Consider a graph G that has a subtree T, and suppose all vertices outside of T have been assigned output labels. Here, T is a bipolar subtree of G in the sense that only the two designated vertices of T have neighbors outside of T. Now, let G prime be the result of replacing T by another bipolar tree T prime that is in the same equivalence class as T. Then the partial output labeling of G can be completed into a complete legal labeling if and only if we can do so in G prime. Intuitively, this allows us to reduce the task of finding a legal labeling of G to that of G prime. It can be shown that the number of equivalence classes is finite. And so we can have a pumping lemma, which allows us to extend the length of a bipolar tree to arbitrarily long that is also in the same equivalence class, as long as the length of the given bipolar tree is at least the pumping constant. Now, let me briefly describe the proof idea of Baliu et al. For the square root of n to linear in n gap. The proof uses the pumping lemma and the following decomposition, which partitions the vertices into three layers. The first layer consists of trees of height square root of n. The second layer consists of paths with constant length that is at least the pumping constant. And the third layer consists of trees of height square root of n. This decomposition can be constructed in square root of n rounds deterministically. The components induced by the vertices in the first two layers are bipolar subtrees, in the sense that only the two designated vertices in this subtree have neighbors outside of the subtree. So we can apply the pumping lemma on them to get a virtual graph. Let W be the target length of the pumping lemma, then the virtual graph will have linear in W vertices if we omit the dependence on n. To establish the square root of n to linear in n gap, it suffices to do the following. Given a sublinear round algorithm A, design a square root of n round algorithm A prime that solves the same problem. Algorithm A prime simply computes the virtual graph and then simulates the given algorithm A on it. Using the definition of the equivalence relation, we can transform a legal labeling of the virtual graph to a legal labeling of the original graph. It can be shown that this can be done in square root of n rounds because the trees in the decomposition have diameter square root of n. Note that if we choose W to be sufficiently large, depending on n, then we can ensure that the runtime of A on the virtual graph is much smaller than W. Therefore, the simulation can be done efficiently, as the vertices at the two ends of the bipolar subtree resulting from the pumping lemma do not need to communicate with each other. So, how to extend this proof to other gaps? The decomposition of Ballou et al. Can be generalized to arbitrary positive integer k as follows. The decomposition has two k-1 layers, alternating between trees of height n to the power of 1 over k and paths of constant length. For any constant positive integer k, such a decomposition can be computed in n to the power of 1 over k rounds. At a very high level, we will follow the similar proof idea of Ballou et al. That is, we want to apply the pumping lemma for all layers C1, C2, C3, and so on. And then we will get a virtual graph of size linear in W to the power of 1 over k-1 if we omit the dependence on n. We will simulate the given little o of n to the power of 1 over k-1 round algorithm on the virtual graph and then transform the legal labeling on the virtual graph to a legal labeling on the original graph. However, we will encounter some issues, and these issues can be resolved using the graph operations considered in the Chang-Petty paper. The first issue occurs when we try to pump the path in layer C2. Recall that the reason that we can apply the pumping lemma to layer C1 is that the components induced by layer R1 and C1 are bipolar subtrees. However, when we consider layer C2, we do not have this property anymore. To resolve this problem, we will apply the duplicate cut graph operation to each bipolar subtree in the previous layer resulting from the pumping lemma. See the illustration in the slide. After this operation, the components induced by layers R1, C1, R2, and C2 become bipolar subtrees. This duplicate cut operation also causes an issue. Remember that our original plan is that we will compute a legal labeling of the final virtual graph, and then we transform this legal labeling into a legal labeling of the original graph. To do so, we need to make sure that if we start with a legal labeling of the graph resulting from the duplicate cut operation, then we can get a legal labeling of the graph before this graph operation efficiently. In general, this is not doable because the output labeling in the two copies of the bipolar tree might not be compatible. This issue can be resolved by letting the vertices near the middle of the bipolar tree to first decide their output labels before we do the duplication. Therefore, instead of computing the output labeling after constructing the virtual graph, what we will do is to fix the output labels of some vertices during the process of constructing the virtual graph. We just need to make sure that the partial labeling can be completed into a complete legal labeling. To ensure this, we compute the partial labeling by simulating the given distributed algorithm. In the construction of the virtual graph, we will need to deal with partially labeled graphs, and so the definition of the equivalence relation and also the pumping lemma has to consider bipolar trees that are partially labeled. The proof sketch that we just described does not immediately give us a decidability result, because to obtain the desired n to the 1 over k round algorithm A prime, we need to be given an little of n to the power of 1 over k minus 1 round algorithm A, and it is not immediately clear how to do so without the given algorithm A. In fact, this is impossible in general. For example, we know that any sublogarithmic round deterministic algorithm can be accelerated to run in just log star n round on bounded degree general graphs, but it is an undecidable problem to distinguish between LCL problems that have deterministic complexity O of log star n and omega of log n, even on grids. However, for our case of the gap between n to the power of 1 over k and n to the power of 1 over k minus 1 on bounded degree trees, with a little more work, we can show that given an LCL problem, it is decidable which side of the gap the problem belongs to. More specifically, given a description of an LCL problem, there is a sequential algorithm that either outputs an n to the 1 over k round algorithm or proves that such an algorithm does not exist. In fact, this is a very hard problem, as in this work, we prove that this is EXPTIME-hard, and so there is no hope to get a polynomial time algorithm for this task. This EXPTIME-hardness proof is a natural extension of a p-space hardness result by Baliu et al. In Part C last year. The EXPTIME-hardness proof is based on a reduction from the well-known EXPTIME-complete problem that, given a linear space-bounded alternating Turing machine and a string, decides whether the machine accepts the string. The key idea of the reduction is that the execution tree of an alternating Turing machine can be verified using locally checkable rules. Let me briefly describe the high-level idea of the reduction. We will fix two LCL problems. One has constant round complexity, the other has linear round complexity. If a vertex in a graph happens to be a root of an execution tree of the given machine and the given string, and it is a rejecting execution, then such a vertex is required to solve the difficult linear round problem. And this case can only occur when the given Turing machine rejects the given string. The rest of the vertices only need to solve the easy constant round problem. Therefore, distinguishing between constant round and linear round LCL problems is EXPTIME-hard. For potential future work topics, there are still a few interesting open questions about the complexity landscape of LCL problems. For example, do we have the constant to log star gaps on bounded degree trees and grids? And what is the complexity of distributed Lovász local lemma? That's it for my talk. Thank you for listening. I'll be happy to answer any of your questions.